Today we're going to see the power method, which is an algorithm that finds approximate eigenvalues and eigenvectors of graphs. Together with the sweep algorithm from 1 week ago, this will give a complete description of an approximation algorithm that is efficient and practical, that finds non-expanding sets when they exist. Then in the second part of the lecture, we're going to see some additional algorithmic applications of spectral graph theory. We will see how to find several non-expanding sets if they exist, how to find a small non-expanding set if it exists, and how to find a nearly bipartite partition of the vertices of the graph if it's possible. So those algorithms will give efficient approximation algorithms for clustering problems, for the small set expansion problem, and for the max cut problem. We now describe the power method to find approximate eigenvectors and eigenvalues for a given matrix. At first, we will describe the method to find the largest eigenvalue of a given matrix, approximately, and then we will see how to adapt it so that you can find the second smallest eigenvalue of a given matrix, approximately, with the corresponding approximate eigenvector. Because in order to run the sweep algorithm for spectral partitioning, we need to have an approximate eigenvector of the second smallest eigenvalue of the Laplacian of the given graph. So here we will assume that the input matrix is symmetric and such that all the eigenvalues are greater than or equal to 0. Such a matrix is called a positive semidefinite. If we have a symmetric matrix that is not positive semidefinite, it's often possible to make it so with some normalization. Now for a symmetric matrix, the largest eigenvalue is the maximum of the Rayleigh quotient of x over all non-zero vectors x. And every maximizer here is an eigenvector of lambda 1. Now we will not be able to solve this problem exactly, so we will not be able to compute lambda 1 exactly and to find an actual eigenvector of lambda 1. But we will be able to do the following. We will find some vector x with the guarantee that the Rayleigh quotient of x is at least lambda 1 times 1 minus epsilon. And then the running time will depend on epsilon. X will not necessarily be an eigenvector. It will just be a vector with a large Rayleigh quotient. But for most applications to spectral graph theory, one usually doesn't need an actual eigenvector, but one or more vectors whose Rayleigh quotients satisfy certain relations. The running time of the algorithm will be nearly linear in the number of non-zero entries of the matrix. So when this matrix will be the Laplacian matrix of a graph, the number of non-zero entries will be the number of edges of the graph. So in that case, the running time will be linear in the number of vertices and edges of the graph up to some logarithmic factor. And then unfortunately, it will also be multiplied by 1 over epsilon, where epsilon is this accuracy parameter. As we will see, this could be a problem in some graphs. The algorithm is extremely simple. It just picks at random a vector with plus minus 1 entries. So every entries will be with probability half minus 1, with probability half 1, and this random choice will be independent for different entries. And then we just multiply x by the kth power of m, where k is chosen to be logarithmic in n. And we will prove that just this computation will give us an output vector whose Rayleigh quotient is close to the largest eigenvalue. It's at least 1 minus epsilon times the largest eigenvalue, provided that k is chosen like this. Now in terms of the running time, to do this computation, we just need to do something like this. Just repeatedly multiply m by the vector that initially is the random vector. Now what is the time that it takes to multiply a matrix by a vector? It can certainly be done in time order of n squared if m is a n by n matrix. But in fact, each iteration can be executed by only applying n plus m operations. So this will have to be then multiplied by k, which is the number of iterations, to give the overall running time. And when k is chosen like this, the running time will be what we claimed in the previous slide. So why is it only order of n plus m time to multiply an n-dimensional vector by a n by n matrix that has only m non-zero entries? Well, we can just look at the computation. So to compute a generic entry of the product, we will need to multiply the corresponding row of this matrix by this vector. So compute the inner product of this row by this vector. Now, if this matrix is given in a compact representation, where instead of for every row having a n-dimensional vector that gives the elements of the row, we just have a list of the non-zero entries of that row. Now this inner product can be computed in time, which is just big O of the number of non-zero entries of this row. So the total computation will be the summation over the rows of the number of non-zero entries of that row. So overall, the running time will just be order of the number of non-zero entries of the matrix. So it remains to argue that this very simple computation will indeed give us a vector whose Rayleigh quotient is at least 1 minus epsilon times the largest eigenvalue. Well, let's say that this is a orthonormal basis of eigenvectors for M. And let this be the corresponding eigenvalues. Here we'll sort the eigenvalues from the largest to the smallest. Here is the first claim of the analysis, that when we pick a random vector, if we then write down, just for the sake of the analysis, the vector as a linear combination of the eigenvectors of M, then the component of the vector that we chose randomly, which is parallel to the eigenvector of lambda 1, is at least a half, with probability at least 3 over 16 over the random choices of x. So for at least a 3 over 16 fraction of all the plus 1 minus 1 vectors, the component of that random vector parallel to v1 has length at least a half. So let's see why this is true. Let's call the coordinate of v1 through vn. Then the component of x parallel to v1 will just be the inner product of x and v1, which will be the summation over the entries of the product of xi and vi. Here each xi is equally likely to be plus 1 or minus 1, and the different entries are independent. So from now on, we will think of a1 as a random variable described by this expression, and whose sample space is the set of choices for the vector x. So we immediately see that the expectation of this random variable is 0, because we can use linearity of expectation to see that the expectation of a1 is the summation over I of the expectation of xi vi. That's equal to vi with probability half minus vi with probability half, and so it's 0. But a1 is not always 0, because the expectation of a1 square is 1. Because again, we can just write down what is a1 square. It's this expression times itself. Then we apply linearity of expectation, and we can see that this is the summation over ij of vi vj times the expectation of xi xj. Now when I is different from j, the expectation of xi times xj is the same as the expectation of xi times the expectation of xj, because xi and xj are independent. Now both the expectation of xi and the expectation of xj are equal to 0, so the product is equal to 0. But when I is equal to j, then here we have the expectation of xi square, and whether xi is plus 1 or minus 1, xi square is always equal to 1. So when I is equal to j, this will be vi square times 1. So the whole expression is just summation over I of vi squared, which is the square of the length of v, of v1. v1 was one of the eigenvectors in a basis of orthonormal eigenvectors, so its length is 1. And let's do one more moment of this random variable, and then it will be a standard calculation to see why this random variable has to be reasonably large reasonably often. So finally, let's look at the expectation of a1 to the fourth. This will be the expectation of this expression multiplied by itself 4 times. So this will be the summation over I, j, k, and l of xi, xj, xk, xl, vi, vj, vk, vl. And by applying the linearity of expectation, we can push the expectation at the end of the expression. Now when, let's say, I, j, k, and l are all different, here xi, xj, xk, xl are independent, so this expectation is the product of the expectations, and it's 0. This will also be 0 if 3 of the variables are equal to each other, and another one is different. For example, when this collapses to xi cube times xl. Because again, we have a product of 2 independent random variables, x1 cube and xl, and they are both equal to 0. The only cases that don't cancel out are those where either all these 4 indices are the same, so we just have xi to the fourth, which is always 1, or when 2 of them are equal, and then the other 2 are also equal to each other, and those 2 pairs are distinct. So for example, if I is equal to j and k is equal to l, we're going to get xi square times xk square. So in all those cases, the expectation will be 1. So how do we account for those cases? Well, there is one case that is simply the expectation over I of vi to the fourth. That's the case where I, j, k, and l are all equal to each other. The other case, that needs to be multiplied by 3 to account for all the way the 2 disjoint pairs could be chosen out of the 4 elements. Summation over I different from j of vs squared times vj squared. Then to go from here to here, we notice that this expression is almost the summation over I of vs squared all squared. The only difference being that here we also look at the case where I is equal to j. So if we subtract minus 3 summation over I of vi to the fourth, this case becomes this case. And then minus 3 summation over I of vi to the fourth plus summation over I of vi to the fourth will give us minus 2 summation over I of vi to the fourth. We know that summation over I of vi squared is 1, so this is 3. We are subtracting some positive quantity, and so the whole thing is at most 3. Now the inequality from probability theory that we're going to use is called the Paley-Zygmund inequality, and says that if we have a non-negative random variable, then the random variable reasonably often is at least some constant times its expectation. The proof of the inequality is in the notes, and it's a fairly standard fact. Now we're going to apply this inequality to the random variable a1 squared. Because remember, we wanted to get an estimate of the probability that this coefficient a1 was at least a half. Well, that's precisely the same as saying that the square of that coefficient is at least a quarter. Now let's apply this inequality where z is a1 squared. So this will be bigger than 1 minus, in this case, a quarter, all squared. And then we have to multiply by the expectation of this random variable, all squared, divided by the expectation of this random variable squared. Now the expectation of a1 squared, we computed it to be 1, and the expectation of a1 to the fourth, we computed it to be at most 3. So the whole thing is at least 3/4 all squared times 1/3, so that's at least 3/16.